Okay. And again, guys, what I'm going to try to do here is limit our time here to 45 minutes on this. So without further ado, I'm going to go ahead and go over these answers. So what I tried to do here, now that we're getting towards the end of the semester, is to start reviewing some things. This one is obviously chapter 1. And basically, to show that this function is continuous, we need to show three things. Number one, we need to show that the limit as x goes to pi of f of x exists and is some number, we'll call it L. Number two, we need to find the value of the function at pi, and that should be some number, I'll just call it, we'll call it capital C. And then number three, number one and number two have to be the same. And just as a quick reminder of, I'm going to go ahead and turn the screen off of you guys, if that's okay, because I can't even concentrate with this thing flickering. Maybe. Okay. All right. Okay. So it turns out that the limit is pi squared plus 3, and we would do that on the left and the right hand side of pi, and you'll see that both the left sided limit and the right sided limit is pi squared plus 3, which is a real number, so the limit does exist. Number two, it turns out that the value of the function with pi plugged in is pi squared plus 3. And then clearly number three, you can see that number one and number two are the same. Therefore, this function is continuous. Now, there is a shorter way to do this particular problem. And if anyone would like to write down in the chat of how you could do this problem in one step instead of having to do 3 steps, I would love to see your response. In fact, it might be worth a verbal gold brick. Okay, question number 2 says to evaluate this limit as x goes to pi of f of x minus f of pi divided by x minus pi, and I'm just going to go ahead and tell you that that answer turns out to be, if I'm not mistaken, I believe it's 2 pi. I believe it's 2 pi. And then question number 3, and this is the question that I'm actually the most excited about, is what does answer 2 represent? Well, it turns out that answer number 2 is simply f prime of pi. It is simply f prime of pi. In other words, this is the formal definition for the derivative of the function. So there's the answers for the warm-up. Okay, so I have 2 important announcements I would like to make here before we move into the lesson today. Number 1 is that next week, a week from today, you're going to have a test on Chapter 3. Chapter 3 test will cover sections 3.1, 3.2, 3.3, and 3.4. In other words, it's the same material that was covered on your last quiz with the addition of section 3.2, which is Rolle's theorem and the mean value theorem. So what I'm telling you is that the test next week does not cover anything that we covered last week. In other words, I'm not going to put any curve sketching questions on there, and it will not cover what we're doing today, which is on optimization. So it's basically stuff we've done at least 2 weeks ago. So next week on Monday, and this is different. Normally I like to give my tests on Thursday, is going to be on Monday. And the reason I'm doing that is because we are getting very close to the end of this semester. So I want to make sure we've got a day or so to review for the final exam. Please make sure you're following the proper protocol when it comes to taking assessments. You need to log in on your school Chromebook. You need to make sure that you have your camera on and your microphone muted and all of those good things. Also, I would encourage you to clean your Chromebook. And when I say cleaning your Chromebook, I mean things like cleaning out the cache and the internet history and all that stuff to make sure you're not running into issues while you're taking the assessment. If you have any questions about that stuff, please let me know and we can chat about that. Okay, the other important announcement I wanted to make is you may have noticed that in Canvas, I made an announcement this morning. That's what you need to check. You need to check that announcement. And this pertains to makeup work. If you have no makeup work, you can just completely disregard what I'm saying right now. But I will mention this date right here so that I can say not only did I post it in Canvas, I can say that I said it in class. Friday, December 11th at 9 p.m. I will not accept any missing work after that moment, so please be aware of that. Okay, moving on. Example number 1, we are now going to look at optimization. And again, I hope that you've already watched my video on this. Also, if you would like this PowerPoint, please let me know. I'll be glad to share this with you. This question is on greatest concentration. It says the concentration of a drug in the bloodstream T hours after injection into a muscle tissue is given by the following equation. When is the concentration the greatest? So this is an optimization problem. And guys, optimization is just a fancy word of saying maximizing or minimizing a function for like a real life problem. So in this case, we've got this drug and we want to know when it's going to reach its maximum concentration. So to do this problem, we're simply going to use the content that we've already learned in this chapter, and that is finding extrema. The first thing that I would like to note is that the domain here is going to be t greater than 0. So we're just interested in any t value that's greater than 0. And this is true for any of those values. As long as t is greater than 0, we're good to go. So the first thing we're going to do is we're actually going to do the first derivative, which is to take the derivative of this using the quotient rule. And instead of taking time to actually do the quotient rule, I'm going to assume that you're familiar with that. You're going to get the following. And you're probably not too surprised by that denominator, but the numerator, there was some cleaning up, if you will. So I don't want to spend a lot of time on that because that's stuff we've already done. But you can clean up the numerator. It turns out to be a difference of squares, and we get the following. And so now here comes the key step. We want to set this first derivative equal to 0. And the reason we want to set that equal to 0 is we want to try to find critical numbers. So here it looks like our critical numbers, well, there's 2 of them. This one right here is when t is 4, and this one right here is when t is equal to -4. Now I claim we can go ahead right now and get rid of the -4. And you probably can understand why that is, because our domain is all values of t greater than 0. We're not going to somehow magically, get a maximum before we made the injection. So in other words, what we're saying is it looks like our critical number here is t equals 4. So let's go ahead now and use our first derivative test. And if we have our first derivative here, I'll call it this is c prime, I'm sorry, let's call it c prime. Only number we're going to put on here is 4. And when we look at that, it turns out that if we pick a number that is less than 4 and more than 0, so let's say 2, if I plug a 2 here, that's going to be positive. So I get a positive times a positive times a positive. That makes this positive, which means that the function c is increasing to the left of 4. Now, if I pick a number bigger than 4, let's say 6, that's positive times a negative times a positive, again, divided by a positive. That's going to give me a negative, which means it's going to be decreasing when we get past 4. In other words, we can go ahead and conclude that the concentration is maximum at t equals 4, and I think this is in hours. Yes, this is in hours. So there's a very simple example of an optimization problem. Given this formula, we needed to optimize it. We needed to find the maximum in this case, and we did that using the first derivative test. So this is, in a way, this is actually just a continuation of what we did in section 3.3. Now, in reality, most people aren't going to come up to you in the real world or in the business world and say, hey, here's an equation. I want you to maximize it. You're going to have to actually figure out the equation is on your own. So that's what this next example is going to be about. So example number 2 here is maximizing area. And it says a farmer with 4,000 meters of fencing wants to enclose a rectangular plot that borders the straight portion of a river. If the farmer does not fence along the river, what is the largest rectangular area that can be enclosed? So this is where things get a little dicey for students. In the previous problem, it's clear what you're trying to maximize or minimize. I gave you the equation. In this problem, you're not given anything. In fact, the only number that's given is this number right here. There are no variables given and no equation. So you as the student then have to come up with all of those things. By the way, this picture here was just to kind of give you some example of maybe a river that's completely straight. And obviously it's kind of a contrived example. But the idea is that you somehow don't need fencing over here along this edge. So this rectangular region, this is what we're trying to do. So just for the sake of argument in this example, and there's more than one way to do that, I'm going to let this length here be x, and that's the bottom length. And when we normally think of the x-axis, it kind of goes in that direction. So if that's x, I bet you can probably guess what variable I'm going to put on this side. And by the way, it's not going to be x because this is x. So I'm going to let this here be y, let's say. And that if that side's a y, well, then this side is a y as well. So if we know that there are 4,000 meters of fencing, so we automatically know that x plus 2y has to be equal to 4,000. That's the first thing that we know. The second thing that we know is, or what we want to know, is we want to know what's the largest area. So now I'm going to need an area function. And hopefully you remember that area is just length times width, or base times height. So in this particular example here, length times width here, well, I think length times width would just be x times y. So we have two equations. In fact, let me label those equations. Here's equation 1, and here's equation 2. Now, if you watch my other YouTube video on doing these optimization problems, you will know that one of the equations is what we call the quote-unquote primary equation, and the second equation is quote-unquote what we call the secondary equation. It turns out that this is going to be our primary equation, and the reason it's the primary equation is because that's what this question is asking about. This question is asking us to maximize the area. So what we're going to want to do is we're going to want to somehow use this secondary equation. This is the secondary equation. We're going to somehow plug that into there to reduce this down to one variable. And I'll go ahead and just do that on the next slide here. So remember, we have this equation a equals x times y. And then for our secondary equation, I think it was x plus 2y equals 4,000. And so I could very easily substitute in for x or y. And I think in this example here, I'm going to solve for y. So I'm going to say that 2y is equal to 4,000 minus x. And then y is going to be equal to, and then that's going to be, I could divide the whole thing by 2, or I could just go ahead and write this as 2,000 minus x over 2. Now, the reason I'm doing this, again, this is the secondary equation, right? This over here was our primary equation. Now what I can do is I can put this into this equation. And in fact, I'll do this in a different color. So I'm going to say that a of x is x times, and instead of y, I can put this 2,000 minus x over 2. In other words, the a of x function is 2,000x minus x squared over 2. This is the equation that we're going to use. Now, guys, I'm going to just let you know right now, this is a very straightforward problem, but until you've practiced a few of these, this is really difficult for students. You need to practice it, and it's very common. You're going to be given two equations, and notice they didn't even give us the equations. We had to kind of come up with them using some basic mathematical facts that we know from the past. And then what you're going to do is you're going to use that secondary equation to write this equation in one variable. You probably can guess why I picked the variable x, because that's what most students feel good about using. So now we are trying to maximize this. Again, we're trying to maximize. Remember, the first problem we were trying to maximize concentration. Here we're trying to maximize the area. So that's what we're going to do. And again, I'm going to go ahead and use the first derivative test. This is going to work out very nicely. So the derivative of this is 2,000 minus x using the power rule. So I didn't even need to do anything special here. Oh, I guess I should have mentioned one other thing here before I forget to mention this now. I did it on the last one, and I should have here as well. Let's see here. In this particular problem, like, let's go back to this original problem. How much fencing do we have? We have 4,000, right? I claim that the domain of this function is 0 less than equal to x less than or equal to 4,000. That's going to be our domain, okay? In fact, we could even go further than that, but we'll just stick with that. We could be even more restrictive. You can't have x equaling 0, for example. Okay, so here we go. We want to set this equal to 0. Clearly, the critical number here is going to be x equals 2,000. So again, we're going to look at a prime. We're going to look at 2,000. If I pick a number that's less than 2,000, this is positive, which means it's increasing. If I pick a number that's negative or past 2,000, it's going to produce negative for the first derivative, which will tell us that the area function will then be decreasing. So therefore, we can conclude that the maximum area is going to be achieved when x is equal to 2,000. Now, if x is 2,000, how are we going to figure out what y is? Well, we can use either of these equations. I'm going to go ahead and use this equation up here, our original equation for the second variable. So if I put 2,000 in here, subtract it over, that's going to be 2,000, and then divide by 2, that's 1,000. So that's going to be 1,000 for y. So a simple basic substitution will give you that. And by the way, the area function, when x is 2,000, that's this equation right here. When x is 2,000, turns out to be 2 million, and I think the units here were meters squared. So there's your maximum area. That's the x value that will produce it, and that's the y value that will produce it. So again, to summarize kind of what we did here in this problem, we wanted to maximize the area of this, obviously, again, contrived problem. We've got this rectangular area that we're trying to maximize. We have 4,000 meters of fencing. I let this be x, these two sides be y. Therefore, the perimeter equation, the secondary equation, was x plus 2y equals 4,000. Again, I didn't put an x up here because of the river. And then the area function, which is what we're trying to maximize, is simply length times width, which is x times y. I solved for y in the secondary equation so I could plug it back into the primary equation. This gave me a very nice expression or equation in terms of one variable x with a domain of 0 to 4,000. And then I went ahead and did my calculus, which is to use the first derivative, use my first derivative test. Turns out the critical number is 2,000, and that gave me the information that I needed. Okay, before we move on to my final example, I would like to have you do a poll. Hopefully I can get this to work. And the poll should be launched now. Okay. All right. So as you guys finish filling out the poll, basically all I'm doing with the polls is seeing who's paying attention or not. And I tried to do a pretty easy equation there. So this last example, I'm going to be using my graphing calculator, and I'm going to try to model that. And I will say that, part of my job here is to not only maximize or help you understand like how to do the calculus, but it's also to make sure you know how to use technology. And I think now that we are virtual and you guys are taking quizzes and tests online, I think that it's even more important for me to be able to teach you guys a little bit of this stuff with the calculator. So as I get into this problem, I'm going to switch over to the Wabbit application. Hopefully you guys will be able to see that clearly. But if not, if you have questions after we're done with the class, you can stick around and ask me, and I'll be glad to help you. So this problem's a little bit more involved than the first two. Honestly, the first two questions are pretty straightforward, standard optimization problems. So it says a small island is 3 kilometers from the nearest point in the straight shoreline of a large lake. Again, it's kind of contrived. We're pretending everything's straight. A town is 12 kilometers down the shore from the same point on the shoreline. If a person on the island can row a boat 2.5 kilometers per hour and can walk 4 kilometers per hour, where should the boat be landed so the person arrives in town in the shortest time? So what I'm going to do here is, now this problem is even worse than the last problem, because this problem, there's no picture given, there's no equations given, and you've somehow got to figure out how to maneuver this problem. So the first thing I want to do is kind of sketch a photo, or not a photo, sketch a picture of this. Let's go ahead and do it in black here. And what I'm going to do is I'm going to draw a right triangle. So this is a right angle triangle. And I'm going to call this point up here, I'll call it I. And I'll put a point up there. That's the island. And then on the shore, there's some point, we'll call it P. And this is the nearest point. So this is the first part of the question. And we know that this distance here turns out to be 3 kilometers. We also know that down the way, there's another point. I'm going to call it T, and it stands for town. And so the issue that we're dealing with in this particular problem is as follows. And let me do this in blue. The idea is this. Since this is the island and this is the town, if to go from P to I, you would have to swim, or I'm sorry, you'd have to row your boat. And when you row your boat, you can only row the boat at 2.5 kilometers per hour. However, you can walk faster in this scenario. So in this distance here, turns out to be 12 kilometers. I'll do that in red. This total distance here is 12 kilometers. So the idea is since you can walk faster than you can row the boat in this example, you're trying to figure out where this point is right here to minimize your travel time. You want to minimize your travel time. So what I'm going to do here is this. I'm going to make up a variable, and let's do it in green. I'm going to call this distance right here x. And that is the distance from the point P over that I want to try to figure out in order to minimize this time. Now, if this distance is x and this distance is 12, then this distance here is simply going to be 12 minus x. 12 minus x. And then I've got one more thing that I need to kind of figure out, and that's this distance here. What's that distance going to be? Well, that's actually pretty easy to see since we've got a right triangle here. We could just do the Pythagorean theorem. This distance here turns out to be the square root of x squared plus 3 squared, or 9. So I claim that the distance that we're dealing with here is going to be as follows, and I'm going to do this in red. Distance is going to be this length, which is the square root of x squared plus 9. And then I need to add this distance here. So we're going to go this length, but we also have to go this length. So that's going to be plus 12 minus x. This is our distance function. Now, the trick with this question is this question isn't just asking us about minimizing our distance. Because, by the way, if we wanted to just minimize the distance, we would just go from t to I directly, right? Because that is the direct straight line path, which is always the minimum value. So what we need to do now is we need to figure out what rate means. So, for example, when we talk about this 2.5 kilometers per hour, well, that kind of gives us the definition of a rate. It's the distance over the time. And so we want to minimize time. So, and I'm going to write this as d over t. So t, if I multiply t over, is going to be equal to d divided by r. This is going to be the key concept to help us in this problem figure out how to minimize our time. So what we need to do here, and this is going to be our main equation that we're going to deal with, is d is going to be equal to this distance, which is x squared plus 9, divided by the rate corresponding to that. Well, we'll notice that this is this hypotenuse, so we'll be in the water. So the rate that we're going to be dividing by in that case is the rate we're going to travel over the water, which is 2.5. Similarly, we're going to move on, and this part over here where we are walking, that rate is 4 kilometers per hour. So this is the equation that we are going to deal with. Now, you can look at that equation and you can probably think to yourself, wow, that does not look like a fun equation to do calculus on. And that's why I'm actually doing this example, because I'm going to actually use my graphing calculator to help me. So if you have your graphing calculator, I would encourage you to plug this into your graphing calculator now. I'm going to do it on the screen as well. And my hope is that you guys are going to be able to see my screen clearly enough. So I'm going to exit out of this for a second. I'm going to keep. And now I'm going to go to my Wabbit program. And I'm going to try to turn this a little bit. Hopefully you guys can see that. Emily, or actually Dagan. I can see Dagan very clearly. Dagan, can you give me a thumbs up? Can you kind of see Wabbit there? Thumbs up or thumbs down? Thumbs down.
Like super blurry.
Okay, super blurry. Okay, I'm going to try turning a light out, see if that helps. Does that help, Dagan?
Yeah, a little bit.
Okay, I'm gonna move it over here a little bit too. Does that make it better?
Yeah.
Okay. All right, guys. So all I'm going to do now is I'm going to plug in that information that we just talked about. I'm going to go into y equals, and I magically already have it plugged in. So all I did is I plugged in that equation that I wrote on the PowerPoint just a second ago, which is the square root of x squared plus 9 divided by 2.5, etc. Now I'm going to go ahead and go into my window here. And I'm not interested, x isn't going to be negative, x has got to be a positive value. So I'm going to basically just start from 0. And then for the max, well, that length at the bottom is 12. So I shouldn't have to go any further than 12. And then for the y min and y max, I think I'm just going to go from 0 to, actually, you know what? Let's not go 0. Let's go from -1 to 5. I'm kind of guessing here a little bit, but let's see what that looks like when I graph this curve. Hey, that's not too bad. It's way up here, but we can see the curve, so that's nice. Now what I'm going to do, and this is what I wanted to kind of show you guys, is I'm going to do something here in Y2 that I haven't shown you guys. I don't think I've shown you this before. I posted a video up in the graphing calculator portion of Canvas, in case you haven't watched that, you might want to make a note of that. What I'm going to do now is I'm going to graph the derivative of this function, okay? So to graph the derivative, I'm going to go to Math, and I'm going to go to number 8, and that's called inderiv, or numeric derivative. So it's going to look like this. It's going to say dd, and I want to put an x in there. So it's going to be ddx. And now if you want, you can retype this equation that you have in y1. I'm just going to put y1 in there. So you can go to vars, go to yvars, and go to y1. And instead of having to type all of that in there, it'll put y1 in there. And then the last thing I'm going to fill out here is this x here. I want to do it for all the x's. And now I'm going to go ahead and I'm going to hit graph. Now you'll see that down here, the graph is underneath the x-axis, and then it comes above the x-axis. It looks like it's staying above the x-axis. Yes. And what I'm interested in, if you remember by our first derivative test, we are interested in when the function's derivative changes from, well, let's see, in this case, since I'm wanting to minimize, I want it to go from negative to positive. So what I'm going to do here is I'm going to change my window here a little bit, and I'm going to go from, let's say, -1 up to +1. I want to see a little bit more detail of just the first derivative. So right now, the graphing calculator is actually graphing the first. There we go. There's the first derivative graphing. And I am looking for where this graph, this is d prime, crosses the x-axis, which looks like right around there. So let's go ahead and see if we can find the 0 by going to second function, trace, calculate. And I'm going to go to number 2, which is 0. You probably remember this from pre-calc. And you just need to arrow over, and I need to make sure I'm on the, you need to make sure you're in y2 by hitting the down arrow. If I'm up here, that's y1. I don't want y1. I want y2, which is the derivative, and I want to be to the left of where it crosses the x-axis. And now I am, and now you can see I'm below the x-axis. I'm going to hit enter. I'm going to go to the right of where it crosses the x-axis, and there we go. Hit enter. It says guess, which I don't want to guess. That's why I'm using a calculator. And it tells me that the 0 is at 2.4019. So what I'm doing basically is I am using the first derivative test with my calculator to help me find the answer. So again, let me kind of go through that process. In y1, I plugged in my function for the distance. Oh, actually, it should be t, shouldn't it? I'm sorry, that should be a t and not a d. This is our distance function divided by our rate, so this is the time function. Then in y2, I did the first derivative of our time function. Then I graphed the first derivative here, and I found where it crossed the x-axis. That's what I did. So let me come back to this. And let's go to this, and let me fix this problem here. This actually should be the t function. So let me erase. Okay, so there's that. Okay, the eraser is not letting me fix. So let me go forward and back, forward. There we go. This is the t function. This is the time function. This is what we're trying to minimize, or yeah, minimize in this case. That's the time function. This was the distance function, and I changed it to a time function. So let's go ahead and finish this out here. So when I used my derivative of t prime, there turned out to be a critical number. There was a critical number at 2.4019219. I found that with my calculator. So that was right here. I'll just say 2.402. And then it went from, in this case, remember, it was negative here and then positive over here. So that means that the t function is decreasing on this side, increasing on this side. So this is the minimum. In other words, if we went back to our original picture that looked something like this, here was the island, here was the point P, and over here was the point T. This distance here which was X, this distance was X, you basically need to be 2.042, and the units here were kilometers from point P, and this will minimize the time. Okay, great. So we still have 4 minutes left. So I'm going to pause here for a second. I'm going to send you in the chat a link to the exit ticket, and then I'm going to stay on here for as long as you need me. If you have questions. And I already see your polls results here, so that's good. And now I'm going to send you a chat. Maybe. And paste. Ooh. Oh no, that's not what I wanted. Sorry guys, it's now, I think I just hit the shortcut for a poll or a print. There we go. There we go. All right, in the chat, you should see a link for your exit ticket. If someone can confirm if that's live, I would appreciate that.